right, line M2, learning task 1, we're going to take a look at alternator maintenance. They start the whole learning task out here just talking about cleanliness. Now, I know that cleanliness is not really going to be something that we are usually going to be involved in. Usually that's going to go and be the customer. However, for some of you that are going to be working in industrial type of applications, you are also going to go and do a lot of the electrical maintenance. And cleanliness is going to go and make a difference, because anytime we start to get buildup of any sort of a crud on stuff, there's always that chance that we are then going to go and have poor conduction. Particularly when we are looking at something that has got brushed types of electrical conduction. So let's start by going through the components that we should be looking at when it comes to alternator maintenance here. The first thing that we're going to take a look at is going to be the DC field circuit that we are going to go and have. Our alternator does need to go and have a DC exciter of some sort that we are going to need to have on there, because the purpose of this DC exciter over here is that it is going to go and create current that is then going to be able to go and give us that DC field that we need to have on our main alternator so that we can build up voltage. If our main alternator is not building up voltage, it's usually going to be an issue with this field, that the field itself has not been applied for some reason. If all the switches are in the correct position, if the field discharge resistor is completely taken out of the circuit, etc., then really that only leaves us with the actual buildup on the DC exciter itself. It's common that that's where we're going to go and have the problem, is the loss of the exciter, but once we actually get to the exciter, there's a bunch of different ways that these things can go and fault out. Let's go through a bunch of them just really quickly. First one was that we could go and have an open inside of this DC exciter. If we have an open inside of that DC exciter, there will still be a small amount of residual magnetism that's going to be inside of the stator of that DC exciter, which means that we're going to go and generate a very small amount of DC voltage still continuously off of this thing. Low values of DC voltage. Those values of DC voltage are going to get fed to our DC field, and they're going to give us a low output on the outside. It's not going to be zero, but it's probably going to be extremely low. Other issues that we can have are going to be low outputs coming off of the actual exciter. Once again, these could be from the open inside of there, or it could be a open that's happening right over here, where we go from our brushes to our commutator. It's really easy for us to go and lose voltage going across from brush to commutator because we have incorrect brush tension. We've got a commutator that has had too hard of brushes, improper brushes applied to it's worn down or something like that. Or if you have the mica too high in between the commutator, if this thing has run a lot, the commutator will go and wear down. It's designed to be a wearing surface, just a slow wearing surface, but that mica tends to go and lift up, and then we start to get bouncing, a lot of arcing and things like that. Verify that you are making good contact. Clean the commutator if you need to. Clean the brushes. Obviously, everything with the power off and everything locked out, so it's not going to go and rotate or anything like that. But we're going to go and check through all of that commutator and brushes. If the commutator and brushes are good, what you can do is you can disconnect the field winding from the actual armature winding over here, and then you can go and measure through that thing. You can just take an ohm meter, check for continuity, make sure the field itself is not open, as well as you can check it to ground, to the stator itself, to make sure it's not shorted out to ground or anything like that. If the armature, the commutator that we have over here, the brushes, if all of that checks out, and you might have to go through multiple segments on that commutator. If that commutator has got multiple DC segments, what you're going to have to do is you're going to have to go across from component to component. Usually you're going to measure from this one to this one. And there should be a coil that exists between there. You're going to check that coil. Then you're going to go and stepwise, go clockwise or counterclockwise, measure across those two. Stepwise, measure across the next one. Stepwise, measure across the next one. You have to be directly across from each other most of the time when we are looking at these, unless your commutator has its brushes mounted at 90 degrees, which happens sometimes, but it's not the usual. So you can check all the different armature coils inside there. You can check the field coil. If you're still not getting anything, the next thing that you'd want to check would be this field switch, and particularly you want to make sure that that field switch, when the field switch is closing, so this closes over here, you'd want to make sure that that field switch, when it's closing, is opening that little branch over there across to my field discharge resistor. If this is not opening, breaking right over there, then what's going to happen is we are going to go and have a large high wattage resistor that's connected across from line to line, and as a result of that, we're going to go and see voltage sag. We've talked about this before, how our voltage tends to sag away as we load up. If we're continuously supplying the field discharge resistor, we're going to go and see a sagged away voltage on that one as well. Check that. Once you move past the field discharge resistor, next thing to check would be your field rheostats. Rheostats are a common place for trouble to go and develop because they are going to be a sliding type of contact. And it's not always going to go and stay clean. You know, you might have it locked down in one position for years and then it gets moved. And all of a sudden it's going to be moved to a part of the rheostat winding. And the rheostats do have little windings that are exposed that might be, you know, just tarnished from years of not being used. And at that point, you know, you get a poor amount of conduction through it. So check that you have got proper end-to-end conduction through. You can go and place your ohmmeter across here, disconnect once again. You know, if you throw open switches and disconnect one end of every device, you can then go and check with your ohmmeter across it and make sure it's going to be fine. If that all checks out, then the next thing you're going to want to check is disconnect the DC field on here, verify it for continuity, verify it for continuity away from ground. Somewhere along the line, you should find something in any one of these things that we're talking about over here that has caused you issues, you know, that's not checking out the way that it should. Then fix that. You know, that's going to be where you're developed this problem off of. Other times we have got, instead of these ones, we have the AC alternators that are going to be with a brushless exciter. And a brushless exciter is going to be actually very similar to the alternator that you're going to go and see inside of a car. In fact, a lot of generator manufacturers will use car alternators for them because they're already built. So, you know, if GM is going to go and build 100,000 units of this, why not? You know, if you're a generator, there's fewer generators than there are cars on the road. Why not go and take some OEM parts and use them for that? I don't remember which ones use which, but there are some that are direct interchangeable between some genset manufacturers as well as over to the actual alternators themselves. It's a three-phase alternator inside of vehicles too, by the way, for those of you that didn't know that. That gets rectified and then, you know, sent off for the rest of your DC components. So you're going to go and check this one, same deal. If you're not building up voltage on the output, you're going to check, make sure your contacts are closing. If your contacts are closing over there, the next thing you'd want to check is if you have got a rotor field. If you don't have a rotor field, you know that ultimately it is getting fed all the way back from over here. So you're going to go through this thing stepwise once again. If there's a little bit of residual magnetism that is going to go on be on the stator of my exciter, then I should go and generate a small amount of voltage coming off of my rotor. So I'm going to go and check that I have got AC coming off my rotor. I should see frequency as well as I should see voltage. If you have a decent multimeter, you should be able to read frequency. So over here, I'm going to be reading frequency. I'm going to be reading a value of voltage. I'm then going to go and move over to my rectifier, and I'm going to go and check what I have got on the output of that one. This is where things like a oscilloscope really come in handy, because what you could have is you could have that these ones here are all correct, but that this one is going to go and be blown. As a result of that, you're going to go and have, you know, 1/3 of the time that we're not going to be carrying current through. So you're going to have a bump, bump, and then it kind of sags down quite a ways, and then it's going to be another bump, bump. And overall, the average value is going to drop down from what we have talked about before, that 1.35. I don't know if you guys remember form factor from AC rectifiers, but it's going to drop away from that form factor, you know, value of voltage to a lower value of voltage, which obviously is going to go and give us a lower amount of circulating current inside there. You check through these ones over here. You can check each of these individual ones. Once again, to go and test anything, always disconnect at least one side of it so that you're not running in parallel with the rest of the circuit. Otherwise, you can just end up with some major problems on your testing. Let me just show you what I'm talking about. If I'm testing across here and here, I want to make sure there are no parallel paths. Well, if I take a look at it, I see a bunch of parallel paths that could be forced through. I could see this as being a parallel path over there, going across the rotor field. I could also go and see that I'm going to go and have this, you know, going through here and coming back up onto here, or coming back up onto here. All of that would go and be placed in parallel, so I'm going to go and get junky readings. What you have to do is always just disconnect one end of every device before you go and, you know, check it for continuity or anything like that, if you are checking for continuity. Otherwise, you're measuring the overall impedance of the overall machine itself. Check the diodes. They do say improperly biased diodes. This is probably not going to be the problem because this thing's going to come from the factory. It's going to have been checked. However, if you have, taken this thing apart and put it back together, if somebody else has, there is a chance that they could have put the rectifier in backwards or place a component in if it is not already just going to be a 3-phase rectifier. A lot of these just have 3 lines in and 2 lines out. It's going to be a single solid state component because they just don't trust us as electricians to go and hook them up. But for good reason, because right now as we're going through it, a lot of you are sitting there probably saying, oh man, boy am I ever glad that they do that because I feel like I would screw that up if I had to do one of these in the field. So usually we're not going to be able to see the individual diodes necessarily. It's just going to be like a solid epoxy block with 3 lines in and 2 lines out. Or if you can see them, they're oftentimes going to be, once again, just tied together in some way that we don't have to worry about it. But you could have one that is going to go and be blown inside of there. You're going to check all of that if all of this system checks out. So you check your windings inside here, check them for continuity and for grounds. You're going to go and check your rectifiers inside here. You're going to go and check them for continuity, check them for grounds. You can check your DC rotor field in here for continuity and ground. If you have got all of that, that means that this should be generating a voltage, which should be passing through and rectifying to here, which should be feeding something here, which means that I should be starting to pick up values of voltage. If I'm starting to pick up values of voltage, what I should then have is I should have that voltage feeding back out and onto this bridge over here. Once again, it could be a single-phase bridge the way that they have it here, or it could be a 3-phase bridge, which would give me a much more even value of voltage. So it might be fed from 3 lines, and in that case is, once again, just going to be a 3-line box on the incoming and 2 lines on the outgoing. Check that, see what you have for your voltage coming through. It's probably not going to have filtering. Check that your field rheostat is set to a low enough value of resistance. If your rheostat is set too high, we're going to have too little current. We're not going to be able to build voltage. So drop the field rheostat, start this thing up, let this thing build voltage, and then bring it back up, etc. Check the field rheostat for continuity as well. The most common place that these things are going to go and fail is going to be in this little wiper arm over here, which would mean that I still would have a path for current, but we'll be going through all the resistance because none of it's jumping up through that field rheostat. And then last of all, check that exciter field. Once again, disconnect one end of every single component as we go through on these. How do I make contact on these ones over here? Going through onto this one, if I take a look, there was one other component that I should have just talked about over here, and that is going to be the component inside of this one and inside of the other one that is going to go and give us our rotation to the field. Do you guys remember this little symbol over here? I hope you do. That little symbol over there, which was, I'll draw it much larger over here, should look like that. That's going to be your symbol for a brush and a slip ring. We should have brushes and slip rings that are going to be, in the case of this one here, an AC alternator that's got a separate DC exciter, that are going to go and carry that current through onto the actual alternator field coil that we're going to go and have. So check that brush and slip ring. This one over here will not have a brush and slip ring because all of this stuff that's down here is all mounted onto the same shaft. It rotates with the machine itself. But if you do have brushes and slip rings, once again, brush pressure, make sure that they're not too light. If the pressure is too light, you're going to get brushes that are going to bounce. They're going to lose contact, make contact. It's going to be intermittent or something like that. If the brush wears down, you're going to have to increase your brush pressure in some cases. You're going to go and have variable springs that you can just, move a few clicks over to increase that tension. Or if the brush is too worn, just take it out and replace it with a proper brush for that machine. Don't just grab any brush. Make sure it is the proper composition and hardness so that you're not going to damage your commutator or your slip rings, whichever one you have. Stators don't have a lot that can go wrong because the stator is usually going to be a stationary roll of wire, a coil of wire that's going to have hard connections. Double check that the connections are tight because this thing is going to go and be attached to an engine. You are going to go and have, your alternator end over here that's going to be attached to that engine. The engine itself is going to give us a lot of vibration off of there. And if these are not done up tight, you can have some problems with these things. In a lot of cases, these are not going to be done with like morettes or anything like that. What you're going to go and have is you're going to have those eye terminals on the ends. You guys have seen these before. It's going to be crimped on eye. So here's your conductor. This is going to be metallic. It's got a little crimp ring over here. And then it's going to go and have an eyelet on there. What we're going to see inside of a lot of our industrial motor connections and inside of a lot of our alternator connections is we're going to stack a bunch of these together and then we go and stick a bolt through that thing. So we're going to go and have just a regular hex bolt that's going to go through all those rings. On the other side of that, we're obviously going to have to go and thread on some sort of a nut onto that thing. And then make sure that this thing has got washers and that it has got a spring washer inside there as well. Spring washer should go between the nut and between the washer itself. And this is just going to go and provide us with tension if this thing should start to go and slip out. Some guys will Loctite them. You just might have to lose that bolt later on if you change it. But if you know that this is what you want this thing to go and stay as, why not? You could throw a little bit of red Loctite on there. What we do once we bolt all these together is then these things go and get rubber taped around the whole thing. Rubber tape is going to be a special type of electrical insulating tape that is stretched as it's wrapped, and it's going to go and give us an insulating wrap, and then over top of that we're usually then going to go and throw another layer of vinyl tape to hold down the rubber tape. The rubber tape should be self-fusing, like it should tie itself together, it should stick to itself, but it's not always going to go and stay, so you do need that external vinyl. Make sure that those connections on your stator, if they are there, that they have not been sitting up against the side of the panel or something like that, because if you get rubber tape and vinyl tape and it's sitting up against there vibrating, what will happen is it'll eventually just kind of wear through and you end up with a short. You'll often see these things, supported in some way so that we don't have those sitting directly on any piece of metal. Rubber tape, vinyl tape is just not hard enough for these things to, be guaranteed that it's not going to go and wear through. Yeah, there's all sorts of ways that you can go and deal with that. You can tie wrap the actual conductors, around the conductor itself. You don't want to tie wrap around the plastic that you've wrapped here, but you can tie wrap those conductors, to the side, bend them out or something like that. That's about it that you could have on your stator circuit. If you do have a small AC alternator, and we're talking really small, small enough that we can have the revolving armature type, your troubleshooting is going to be mostly focused probably around these 3 slip rings that you're going to go and have, because those 3 slip rings are more than likely going to be the place that you have problem. It's usually brushes and slip rings that tend to be a problem in any sort of a machine breakdown that has them. Double check that you've got, once again, proper brush tension, that you have got, a good amount of patina. That's going to be that layer on top of there. If it's too shiny, your brushes are too hard, or you've got some other type of environmental factor that is creating a loss on those. So just, double check that you have got proper brushes off of these. All right, that is it for our troubleshooting of alternators.